Chapter 16 Nuclear Chemistry. With the production of artificial radioactive substances in 1934, the field of nuclear medicine was established. In 1937, the first radioactive isotope was used to treat a person with leukemia at the University of California at Berkeley. Major strides in the use of radioactivity in medicine occurred in 1946 when a radioactive iodine isotope was successfully used to diagnose thyroid function and treat hyperthyroidism and thyroid cancer. Radioactive substances are now used to produce images of organs such as liver, spleen, thyroid gland, kidneys, and brain, and to detect heart disease. Today, procedures in nuclear medicine provide information about the function and structure of every organ in the body, which allows the nuclear physician to diagnose and treat diseases early. Section 16.1 Natural Radioactivity. Most naturally occurring isotopes of elements up to atomic number 19 have stable nuclei. Elements with atomic numbers 20 and higher usually have one or more isotopes that have unstable nuclei in which the nuclear forces cannot offset the repulsions between the protons. An unstable nucleus is radioactive, which means that it spontaneously emits small particles of energy called radiation to become more stable. Radiation may take the form of alpha, beta particles, positrons, or pure energy such as gamma rays. An isotope of an element that emits radiation is called a radiotope. For most types of radiation, there's a change in the number of protons in the nuclei, which means that an atom is converted into an atom of a different element. This kind of nuclear change was not evident to Dalton when he made the predictions about atoms. Elements with atomic numbers 93 and higher are produced artificially in nuclear laboratories and consist only of radioactive isotopes. The atomic symbols for the different isotopes are written in the mass number in the upper left corner and the atomic number in the lower left corner. The mass number is the sum of the protons and neutrons in the nucleus, and the atomic number is equal to the number of protons. For example, a radioactive isotope of iodine used to diagnose and treatment of thyroid conditions has a mass number of 131 and an atomic number of 53. Radioactive isotopes are identified by writing the mass number after the element symbol, name or symbol. Thus, in this example, the isotope would be called iodine-131 or I-131. Table 16.1 compares some stable, non-reactive isotopes with some radioactive isotopes. Stable isotopes: magnesium-24, iodine-127. Radioactive isotopes: magnesium-23, iodine-125, uranium-235. Magnesium-27, iodine-131, uranium-238. Types of radiation. By emitting radiation, an unstable nucleus forms a more stable, lower energy nucleus. One type of radiation consists of alpha particles. An alpha particle is identified as to a helium nucleus, which has 2 protons and 2 neutrons. An alpha particle has a mass number of 4, an atomic number of 2, and a charge of positive 2. The symbol for an alpha particle is the Greek letter alpha, or the symbol of a helium nucleus, except that the 2 charge is omitted. Another type of radiation occurs when a radioactive isotope emits a beta particle. A beta particle, which is a high-energy electron, has a charge of -1. Because its mass is so much less than the mass of a proton, it has a mass number of 0. It's represented by the letter beta, or by the symbol for the electron, including the mass number and the charge. A beta particle is formed when a neutron in an unstable nucleus changes into a proton. A positron, similar to a beta particle, has a positive charge with a mass number of 0. It represents the Greek letter beta, with a positive 1 charge, beta positive, or by the symbol of an electron, which includes the mass number in the charge. A positron is produced by an unstable nucleus when a positron is transformed into a neutron and a positron. A positron is an example of antimatter, a term physicists use to describe a particle that is the exact opposite of another particle, in this case an electron. When an electron and a positron collide, their minute masses are completely converted to energy in the form of gamma rays. Gamma rays are high-energy radiation, released when an unstable nucleus undergoes rearrangement to particles to give more stable, lower-energy nucleus. Gamma rays are often emitted along with other types of radiation. A gamma ray is written as the Greek letter gamma. Because gamma rays are energy only, zeros are used to show that gamma ray has no mass or no charge. Table 16.2 summarizes the types of radiation we will use in nuclear equations. Some forms of radiation. The alpha particle, symbol alpha, which is a helium nucleus, helium-2, 4. 2 protons and 2 neutrons are emitted as an alpha particle. Beta particles. A neutron changed into a proton and an electron is emitted. It's a negative 1 charge, and it's a high-energy electron. Positron. A proton changes to a neutron and a positron is emitted. Positive 1 charge, high energy. Gamma ray. Energy is lost to stabilize the nucleus. A positron and an electron beta particle collide, forming a gamma ray. A proton is emitted. It's a hydrogen 1 proton. A neutron is emitted. Biological effects of radiation. When radiation strikes molecules in its path, electrons may be knocked away, forming unstable ions. If this ionizing radiation passes through the human body, it may interact with water molecules, removing electrons and producing hydronium, which can cause undesirable chemical reactions. The cells most sensitive to radiation are the ones undergoing rapid division. Those of the bone marrow, skin, reproductive organs, intestinal lining, as well as the cells of growing children. Damaged cells may lose their ability to provide necessary materials. For example, if radiation damages the cells of the bone marrow, red blood cells may no longer be produced. If sperm cells, ova, or cells in the fetus are damaged, birth defects may result. In contrast, cells of the nerves, muscle, liver, and adult bones are much less sensitive to radiation because they undergo little or no cellular division. Cancer cells are another example of rapidly dividing cells. Because cancer cells are highly sensitive to radiation, large doses of radiation are used to destroy them. The normal tissue that surrounds cancer cells divides at a slower rate and suffers less damage from radiation. However, radiation may cause malignant tumors, leukemia, anemia, and genetic mutations. Radiation protection. Radiologists, chemists, doctors, and nurses who work with radioactive isotopes must use radiation protection. Proper shielding is necessary to prevent exposure. Alpha particles, which have the largest mass and the charge of the radiation particles, travel only a few centimeters in the air before they collide with air molecules, acquire electrons, and become helium atoms. A piece of paper, clothing, and our skin are protection against alpha particles. Lab coats and gloves will also provide sufficient shielding. However, if alpha emitters are ingested or inhaled, the alpha particles they give off can cause serious internal damage. Beta particles have very small mass and move much faster and farther than alpha particles, traveling as much as several meters through the air. They can pass through paper and penetrate as far as 4 to 5 millimeters into body temperature tissue. External exposure to beta particles can burn the surface of the skin, but they don't travel far enough to reach internal organs. Heavy clothing such as lab coats and gloves are needed to protect skin from beta particles. Gamma rays travel great distances through the air and pass through many materials, including body tissues. Because gamma rays penetrate so deeply, exposure to gamma rays can be extremely hazardous. Only very dense shielding, such as lead or concrete, will stop them. Syringes used for injections of radioactive material use shielding made of lead or heavyweight materials such as tungsten or plastic composites. When working with radioactive materials, medical personnel wear protective clothing and gloves and stand behind a shield. Long tongs may be used to pick up vials of radioactive material, keeping them away from hands and body. Table 16.3 summarizes the shielding material required for various types of radiation. If you work in an environment where radioactive materials are present, such as a nuclear medicine facility, try to keep the time you spend in your radioactive to a minimum. Remaining radioactive twice as long as they expose you to twice as much radiation. Keep your distance. The greater the distance from a radioactive source, the lower the intensity of radiation received. By doubling your distance from the radioactive source, the intensity of the radiation drops to 1 to the 1/2 to the square or 1/4 of the previous value.